We know that Einstein's theory of special relativity postulates these two things. Firstly, that all laws of physics are the same regardless of the reference frame. In space, for example, an observer traveling 10 meters a second away from his astronaut buddy would be mathematically identical to his buddy moving 10 meters a second away from him. His second postulate tells us that the speed of light is constant no matter the observer and is absolutely invariable. This means that, unfortunately, pushing your flashlight forward does not release photons, which are traveling faster than the speed of light. In order to derive the Lorentz transformation, or the Lorentz factor, which describes how much the time of a moving object will be stretched depending on its motion relative to the speed of light, we must combine these two rules, or postulates, with every physicist's favorite tools, arrows and algebra. Firstly, we will define gamma as the factor that, when multiplied by some time t, will become dilated or stretch time, represented here as t prime. Dividing both sides by t, we find that gamma is equal to t prime over t. Remember this definition. In order to find some analytic solution to gamma, we must draw out a diagram. In our universe, imagine two observers, A and B, positioned like so. Observer A's instantaneous velocity in the x direction is some velocity v, which is a significant fraction of the speed of light, c. When time t equals 0, observer A fires a photon, and to observer A, the light beam travels some distance, vt, or in this case ct, as c is the speed or velocity of light. To observer B, however, she sees observer A traveling some distance v multiplied by the dilated time t prime, and sees the photon draw out a path like this, with velocity c. And as this arrow is physically larger, it means that it too must be multiplied with dilated time. From here we can see a textbook application of Pythagorean theorem, which gets us this equation. We can see the terms t and t prime quite a bit, and I remember us expressing gamma in terms of those quantities. Can you guess what we do now? Our goal here is to rearrange the equation until it looks like this, and taking the reciprocal of both sides, we find the same quantity, t prime over t, as before. This is the Lorentz factor. Have fun with it. Try applying this factor to some basic distance problems and see why we can't notice this phenomena on Earth.